Good to see everybody again. What we're going to do is we're going to take some of the morning session and we're going to build into the next steps of this. So let me go ahead and share. So you should be able to see my talk. Everybody good? All right. If you got it, then let's get on and moving. Oh, I wish. No dancing yet. No dancing yet. Here we go. So guys, when we're talking about using visuals here, one of the higher effect sizes, we called it a moderate to high effect size. A high moderate effect size was on visuals, specifically a concrete visual abstract, a leveled sequence of instruction using multiple visuals based on Bruner's work. If you're looking for more work on this, and I'll show the website later on, Patton actually already has some cool stuff on it. So we're going to take that idea that Patton has, and we're just going to build from it using this as a research-based effectiveness approach that we talked about earlier on today. So I touched on it earlier. I'm just going to move some things aside here. We touched on it earlier, but I want to make sure I'm clear. When we talk about algebra, I had said algebra and algebra 2. You might have heard me say that kind of in brief passing. It's because if you're crinkly like me, or maybe you have well-preserved, algebra used to only be algebra, then geometry, then algebra 2 is mixed with trig and pre-calc. That was the setup. As time has gone on, we have stretched out the meanings of algebra and what to do for algebra. And now we have things such as algebra 2, we have algebra 1, algebra 1A, algebra 1B. So algebra is still the gateway, but now we end up calling a lot of that work algebra 2. We've had several studies in the United States trying to determine why students, even if you make community colleges and technical school free, right, free tuitions, nothing's ever free, but you made that free tuition, why is it that we have such dropout at those levels? And what we have found is that the students will walk in on average with less than an algebra 2 understanding of content. And then they go on and they have to take their assessments or their original math placement, and they're placed a full year, not one course, but 2 courses behind average, which means a 2-year degree just became 3 years. Well, if you want to be some of these important work that we're talking about, like HVAC was here at my house yesterday with a dead AC. Auto body mechanics, auto body has changed. Now that we have electrical cars, you have to be specifically certified in the electrical work to even touch a body panel on a Nissan Leaf or a Tesla. And because of the growing abundance of electrical cars, you have to have that electrical certification. In other words, we have so many more people who need these kind of high-level tech degrees now that we need the stronger math. And I just want to be cautious here. When we're talking about the outcomes, you hear Brad say things like outcomes related, and I am not pushing four-year institutions. I actually think we have a high need of technical school degrees. Those are the people that make or break your system, right? I mean, the guy doing HVAC yesterday was explaining things differently than the guy who installed the system 8 years ago. I'm like, oh my gosh, well, we've been doing this forever. He goes, well, that's wearing on your system. We need people who know what they're doing. It's going to take algebra 2 understanding to get our students to where they need to be. And if you're ever looking for this, you can take a look at Bible, Moral, Edelman, ADEL, MAN. You can take a look at their research from the US Department of Ed. They go through it. All right, so what do algebra teachers, when kids go to algebra, what do they say that students need? Well, they're finding that their background is kind of weak in pre-algebra work. In other words, if they could just blank, blank, and blank, and we'll give those in a second, that would really make it easier. Then we could focus on my content. But without it, I find myself having to teach them up to get to the content that they're currently in. Those areas tend to be, and they nailed it when they called out, right? Fractions, decimals, ratio, percent. That was one. Word problem solving, being able to solve problems in a word format because of the assessments. And then just study habits, knowing when to take notes, how to organize your work. That executive functioning, that became a piece of this. So when the National Math Panel did the National Survey of Algebra Teachers, these 3 things stood out. And by the way, you got it. They still exist. The greatest challenge of all algebra teachers, though, middle school, high school, no matter what, working with students who weren't motivated. Well, of course, right? Because if we have such a large number of students not even at the proficient level, they're not meeting grade level standards, whether or not they get an A or B or C or what, they're still not meeting grade level standards. They move on and they're really not ready for that next grade level. That is hard, because why would they be motivated to do things that they're not good at? That's why when I gave the non-example earlier, I said, talk about what they're doing right before we talk about what they're not doing right in, because we need to keep coaching them into these small steps of math. Well, I do want to share that math progression that from earlier. I'm going to get more detailed on it and show you how this builds up. We found that in preschool, and I'm giving you my citations here. In preschool, early number sense predicts math achievement through late elementary and even some in high school. And Sarah Watt's work has shown that early number sense starts early and predicts a lot, which means before they even get formalized schooling, we can start to see who has potential in math. That's not good. That means it's likely those who are being taught at home, because there is no magical math gene. Yes, there are cognitive characteristics, but without I can't say it, magical math DNA that's truly not there, guess what? Those who are prepped do better. Who learns the quickest in kindergarten, which means they're prepped on this and then they grow in kindergarten? That kindergarten growth can predict the end of third grade, right? And that rate of growth we've even found not only predicts math, but actually in literacy. Kindergarten growth ends up being a better predictor of literacy than early literacy skills alone. Yes, math, the patterns of math and the language of math, more simplified than literacy, but taught in specific ways, that predicts later achievement. Fractions, division, which is based on computational understanding, put into a fractional format, that predicts algebra and high school math proficiency. And think about it, instead of one number representing a point on a number line, now I've got 2 or 3 numbers representing a point on a number line. 3 numbers? Yeah, 4 and 1/5, or 17 thirds. That is now multiple numbers representing 1 point on a number line. That means math gets really complex at fractions. Oh, this is a scary one. Kuhn and Davis did a study of Mississippi and was trying to find out how do we prep students for success? What's the best route to take them to success? And they used the ACT. Every student in Mississippi at the end of the 11th grade takes the ACT. And what best predicts that ACT math score? If you use that as your outcome, the best predictor, they had several other things that we cannot impact, but the best predictor they found was 5th grade, end of grade, which means that by 5th grade, we can start predicting who's going to make it to that algebra 2 level. That's frightening. Just a couple more here. Math proficiency in 8th grade predicts algebra 2 success. And like I said, algebra 2 predicts college entrance, technical school completion, and in other nations even predicts like quality of life measures. Wow, guys, we have got a lot of work. It starts early and it continues. What does that mean for us at the middle school, high school level, since we're secondary right now? That means we have to be thinking about how to shore up past misunderstandings as we get to our construct. So you have to have a clear, full understanding of where they're coming from, which means that even though we're going, well, here's my grade level standards, you better know the breadth. You got to know where they're coming in at so you can know what strategy they use walking in. All right. So here we go. We're going to start. This is our schedule for the day. Every single time we see a dance party, that's the time to answer questions. So I know Julie is going to be looking over the questions. She'll sum up if I missed one. So don't hesitate to use the chat during this. I have overplanned like I always do. So just about an hour from now, yes, so just about an hour from now, we got to wrap this piece up. So here's what we're going to cover. We're going to start with length-based approaches. We're going to use those for fractions, which you may go is or is not. Remember, we're going to start with fractions. So we talk first. We're going to start with fractions and then equations. But I want you to think beyond that. Because this is such a short session, these are my exemplars. Length-based approaches are powerful. So fractions and equations, we're going to show those examples. Think beyond it. Length-based works. It's magnitude. Then we're going to show an area model. We're going to talk about factoring with the area model, but you can go beyond that. Think about how else the area model works. When I showed the examples earlier, the area model, it's really just the distributed property. That's how it works. We're just showing how distributed property works between 2 expressions. Then we'll talk about problem solving. Someone asked earlier, they said, oh my gosh, I want to learn more about problem solving. I hope you're here because we're going to get into specifics of a problem solving approach in secondary math that has recent effects according to Dr. Myers and his team. And we're going to use, instead of SBI, which is more limited on upper level work, right? It's limited to get to upper level work. We're going to do general heuristics, which had nearly the same effect size, but is used across the board. And finally, we're just going to wrap it up with some instructional considerations. Every time we see a picture, that's the question time. So type them in anytime you get them. I'll try to review, but when we get to the schedule and the dance party, that's when we're going to go through the questions. All right, let's get started. All right, I break PowerPoint law here. You got the, because it's too much on one slide, but you got the gist earlier of what are some of the characteristics students bring to it. That was kind of a deficit look. I want to look at the strategic look. Focus on this column. Students who can make visual displays of their information, like a sketch pad in their mind, that's what visual-spatial working memory is. These are students who do better in this. And I believe this comes from my book with Dr. Blackburn on students who, on rigor for students learning in math. Attention to task, students with detailed attention. Well, no surprise, if they have detailed attention, they can pay better attention to things. We are now in a world of weak attention spans. Donna, I can see your wonderful face, but if I couldn't, right, you know how it is with students where they can look at you, but they're really not there. There's but that's how this works. We need them to attend the task, which means we need lots of activities. That's why these conference sessions are odd. You're going to have to think, how do I keep, you know how to engage yourself and keep alert. We need to give breaks for students so they can engage and be active in the math along the way. Otherwise, they have a hard time attending the task. Persistence of task, I think this makes sense. Students who have difficult tasks tend to give up easier, give up more when they have a background of failure. Surprise, surprise, people don't like to do what they're not good at, which means we need to give them little minor successes and cheer sessions, not fake you're doing well. Find out what they're doing well in and hone in on it. And then the last one, strategy. Like we said, students who have a stepwise mathematical process in their head tend to do better in math. U.S. Department of Ed has talked about some of the things that will help that. How do we build that visual-spatial, working memory? Well, we give them visuals to do on a paper, on a sketch pad, on a computer, whatever that is. Students need to create visuals, and they need visuals that are efficient. That means the visuals come from us. Sometimes those visuals are physical manipulatives. I call them concrete objects because it's a historical term, but last kid I did some tutoring with goes, I thought we're playing with concrete. And I'm like, oh, concrete, because I said concrete. She thought we were like brick and mortar. We're going to build a house outside or a wall. I don't know what you, God love her. And I said, oh, I'm so sorry. It's a different kind of concrete. We're not going to melt it down. I want to say we can't. We're not going to melt down the plastic. All right. But remember, meta-analyses show this approach is highly effective with visuals. So number lines are powerful. A physical form of a number line is called a strip diagram. We'll use those pretty quickly here. And any picture representation of a manipulative, also powerful. While you're teaching the steps, connect them to a visual. It helps build a concept. It doesn't make them faster. It helps build concepts. So connect your visual to the abstract steps that a student must be thinking. So here's what we found. Visuals first, core and intervention. With you, Jill. Core and intervention need to use visuals. It is a must. You should make it a non-negotiable. All new complex content that we teach, and even have your list of your big ideas, if you have them at the state level or you have your own internal. I know district directors who write their own internal list. They do their own factor analysis of which standards stand out for their students' learning. If you run that data, those need to be taught with visuals up front. Okay, here's why. It improves your info processing. It aids visual-spatial working memory. And because of that visual, you can have quicker recall. What we found is abstract learning, kids will have it, but they don't know how to recall it in an exact format or order. That's where the visual helps retrieve the right process. And then lastly, teach students how to use the visuals. You can't just show them and say, here's a visual. Remember, graphic organizers from Hughes' work was a low effect size, like a not effective. You have to teach the visual. If you teach the visual explicitly, you will get more out of it. So here comes CVA, and that's where I said Patton has this already, and I can't copy it. I don't know if anybody has a chance to just copy this down, but Patton already has a whole piece. It's called CRA. It's an older term, still works. Same thing. It's just R stood for representations, and they're all representations. So this is a sequence, a gradual sequence of instruction, concrete to visual to abstract. CVA is the highest way we found for using manipulatives. If you want manipulatives, go CVA. That is a great way to do multiple representation at the visual level. So this comes from the U.S. Department of Ed, one of their guidebooks in here. It's my drawing, so make fun of it all you need, but it's 3 plus 1x is equal to 7, right? 3 plus 1x equals 7. So know what your visuals are. we had plus signs. They didn't like my plus signs. I also did the river. It was a string, and the string came for equals. And the US Department of Ed did not like a squiggly line going down their sheet. But the original model that was done in our research study had a string here. The X and actually for the original study, the cup of X, it was a cup, then an X. And they said, but the construct is cup of X. Absolutely. We just haven't put them together because you might have 2 cups of X, 3 cups of X, or heaven forbid, we will do one day 1/4 cups of X. That just means 1 cup over 4 cups. Show it as a discrete fraction. But you would go through these steps at a concrete level, then at a visual level, and then the abstract. But remember, you prepped it. You went through your own abstract approach. How do I set this up? Then you found a visual model that will show that, and you taught it these steps while showing the abstract, then the visuals while showing the abstract, and then the abstract alone. That is how this goes. But I've got just 4 easy things to remember when you do CVA. 1, the steps match per level. Don't add steps or take steps away. If you have a visual that oversimplifies it so that the visuals don't look like the abstract, you've got yourself a non-CVA. That means they're now about to learn 2 different ways of solving the same problem without ever coming to mastery on any of them. That's the problem. IES says, watch out for that. Teach students to mastery at whatever approach you're taking before you move to another approach. Materials need to match the construct, not match your budget, right? If your budget says I've got $400 for manipulatives, don't spend $400 on manipulatives. Cheap things. Look, they copied the exact approach. Popsicle sticks, these are actually cardstock that did an addition. I told you that was a string. This was like bathroom cups. And again, I've used toothpicks before with blunt ends, matchsticks without the igniter. You can look them up. It's just an art supply piece, but use easy things. All you're doing is using these concretes. How often you can use the concrete? 1 or 2 times. Do not do the concrete for an entire day of concrete. Do the concrete 1 or 2 times. It's called expeditiously. And then they wrap up the concrete and then they start drawing pictures. The concrete step, the physical manipulative step is only to set in the visual spatial working memory so they can get to a drawing. The focus of all of this work is to get to abstract. I don't need my kid to be the best concrete manipulator in the world of moving things around. I want them to get to abstract, but I can do that through these steps. And then the last one here, when I said expeditious use of concrete, that helps you get to this. So 1 or 2 times only concrete. You rarely hear that. Most people say, teach it to mastery. Those are called single case design studies. The actual research is designed to take them to mastery before they move phases. That's a single case design approach. Large group designs show it either 1 or 2 steps has the importance. And who wrote that out? Not just US Department of Ed, the National Math Panel, the congressional panel said, don't spend too long on concrete. All right, so those are don't forget to ask questions in there and we'll get to them in a bit. So where is CVA? What is that? We've got lots of studies that CVA is helpful for. And why, for whom, right? Kids with working memory needs, visual spatial needs, and kids who struggle in math, which is a lot of us. We're going to focus on these 2 areas. We're going to start with fractions and then get to equations and factoring. So here we go. Before we get to the examples, are there questions on the CVA or the need for visuals? And I'll do a bad wait time of just maybe a couple seconds here. All right, guys. Boy, that's bad wait time. I'm trying though. Here we go. Let's jump into visuals. And by the way, the Carlton, heck of a dance. You go, buddy. So yeah, oh yeah, work it. Okay, so here we go. Number line approach here. Number lines are where we're going to start. That's the visual we're starting at. And I'm going to show you at a visual, the V level, just the picture representation. Be thinking how I could get a physical model in there. Do I use a sentence strip? Could I have dual sentence strips for something? You got it. Do I just do a number line like on a white, oh, that won't show with this. But anyway, on a whiteboard here. So how will you want to set those up? But it is for conceptual and procedural memory connected. Remember, always connected. Anybody who wants to separate them are either trying to just build engagement because they're worried that the students or they don't understand how to connect the math to the real world. There are real good reasons for why you do those projects and those kind of activities. If it's to teach the construct to mastery, that's not exactly going to show there. it would be for another mean. Intuitive approximations, number lines are great for this level of number sense called magnitude approximations, making sense of size and quantity. They progress from early to more difficult because number lines can be used across multiple contents well through high school. And again, think about what physical manipulations you can use to help excite the students along the way. So one of the ones I use all the time is fraction strips, piece of paper, fold it up. If you like food, you can take the peelable Twizzlers. Oh, I don't know if I like that food, but they peel off and they make, I forget the length, but they all have the same length. Just use a little plastic knife and you can actually separate them out. The reasons why it's important to learn to separate them out is because we know a student here's 1/5 and they have a length, they will put 5 dash marks in between. Fifths, 1, 2, 3, 4, 5, because they're thinking counting. They don't think number as a length, which means 1, 2, 3, 4, 5. They're not thinking 5 lengths, they're thinking 5 cuts. So get them early. That comes from a US issue, right? If I'm on an elevator in the ground floor, we call that floor 1 in this country. Almost every other country calls that 0 floor or G, ground floor. The first floor is actually 1 floor up in most countries, not in the US. So our students in that 0 to 1 don't really understand 1 is a distance. So here's where it comes around, because it won't hurt them too much early on. It won't show, it shows here, which means first, second, third grade can get away with it. They start showing fractions more complex. They're not impacted by the weakness, but the child is. All right. So if I'm going to show them with fractions of how to split them up and what equivalent fractions are, remember, decimal fractions come together. Don't separate them out. That's a language piece that separates them out. It's a language of writing that separates them out. Think about how decimal fractions are done. So I can have, right, what is tenths versus hundredths. So in this case, I've got tenths only. What is 5 tenths, 2 tenths, 1 tenth, which is important for our students to see where those tenths come out. Where fractions, it's hard to notice what gets bigger and smaller, right? Is 2/5 greater than or less than, 1/8, right? Well, the 8 is bigger, but I don't get it. It's the understanding what the denominator means in fraction. It's complex. Think about decimals, help them make the connections with tenths and hundredths first, then start changing that denominator up away from a typical place value into a base 5, a base 4, a base 8. All right, these are just some of the examples that we took from a class, and we have represent 1/4. So we have the fraction strip here. Have them learn to fold it out, right? They fold it half. You can see the folds and half again, and then color in 1. That would be my coloring, not a child's. We took the same approach then. We mirrored it up. We matched it up to an equivalent fraction, and then we did another fold, hard to see the fold, and I dotted out the fold so they would see that fourths match up for the students, but work them in teams. So now 2/8 is the same value or length as 1/4. And same thing down here. Do the same thing with twelfths. Right, that's a lot of folds. You see all the little folds here. And now you want to show them how 3/12 is the same value as 2/8, which is the same value as 1/4. Equivalent fraction starts here. At the visual level, right, if they can do physical models, remember physical models, CVA, that means that the visual model, we have a very similar approach so they can see that out. But it's really hard to make that visual model before you've had a concrete version of it, just to show equivalent fractions. So do think about length-based models when we're showing the equivalent fractions or fractions in general. How does this connect later on? Well, an exemplar would be unit rate, right? 300 meter, the person in their car or in their bike, maybe they're a super biker that I would never be. Oh my gosh, my poor little legs. But they bike 300 miles in 10 hours. Anybody ever do that? Anybody? No, nobody. Okay. But if you did, you get it. And that, what does that mean? How many miles per hour did they go? Funny video still. So in this case, you actually have equivalent lengths. If it is 300 miles in 10 hours, that means the same time it took to go 300 miles was the same time as 10 hours. So we do equally length bars here. This is that same model based on fractions. We're just going to show up for unit rate. So for 300 miles in 10 hours, and now we want to know how many per 1 hour, which means we're going to break it apart, right? Well, I can break it apart to 5 hours. Right now it's 150 per every 5 hours, and then break it down even more per hour. And so again, this same approach mirrors what we did for the equivalent fractions. So we don't need to make equivalent fractions one day, never do anything with it again. And here comes unit rate. divide, right? We can still show the same model to make sense of that process. When you're getting to fractions with multiple denominators, remember, start with tens, build from there. Once we start changing our denominator to not be cleanly with decimal work, now, right, it still works for decimals, decimal fractions, but now we can start having a different conversation. Take a look at this one. What is happening here? You're saying multiplication, but think about how we're going to read this to the student. We're going to say 2/3 of 1/2. So what does of 1/2 mean? That means of my whole 0 to 1, right? Length based, 1 is a group, right? 1 is a distance of my whole. I identify where 1/2 is. I then want to figure out what are 2/3 of the way there. So what do I do for this? I set up each half in the thirds. So now I have 1, 2, 3. I'm trying to do distances. It's hard. 1, 2, 3. I'm sorry, digits get more arthritic as I get older, but I go through my distances. I have 3 distances there now. So that would be thirds of halves. So what does 2/3 of halves mean? Well, I did a bunny hop here, but remember, we're going to also show it length based, and I'll do that in just a second. Show them that bunny hop just so they see it. There's 2 from 0 to 1, 2. Show that distance there. So that right there, that point on the number line is 2/3 of 1/2. Okay. So how do we make sense of this as magnitude? Well, we know in the computation, you could just multiply straight across. One way to do it, right, is be 2/6. Does that represent 2/6? Yes. We're going to show them how it's 2. And down here, 6 groups of a whole. Start with denominator. 6 small groups within a whole. 2 of them are represented in this computation. That's how 2/6 are represented. I suggest helping them see numerator denominator. Put some bar model over it, put a 2 bar up here, and put another bar of 6 underneath it. So they show it's going to be 2/6. If they see it, well, wait, I can group them together by 2s, right? 1, 2, 1, 2, 1, 2. Well, that's the translation for 1/3. All right, let's get more specific. See if I can do it here. 3/4 divided by 1/2 is really how many halves go into 3/4. I actually did this with one of my children in early elementary. Sure, I'd be doing a talk, a very foreign time zone, a foreign country. And so the time zones were messed up. So she was supposed to be in bed, but she was listening to me, right? Outside the door, just right on the other side. And her little ears and pressed against it. She goes, "What were you doing in there?" When it was all done. And I go up in her bed and we lie down. I said, "Well, we're just doing fractions." She had to be like first or second grade. This is my youngest, my very loquacious youngest. And she goes, "Well, give me one, I can do it." I said, "I bet you can." Okay. I didn't ask her what 3/4 divided by 1/2 was. I said, okay, if that's 1, how many halves, right? Halves, let's do your hands in halves. And she's mirroring me. How many halves go into 3/4? And I showed her how to get the 3/4. How many halves go into it? And by logic, she goes, "I don't know, about 1.5 of them." Yeah. So here's how we look at this. Identify where 3/4 is. I put my half in there because it's big, didn't need to do that. But 3/4, right, of 1 whole. And then how many halves? So we mark out at least 1/2 and another section of another half goes into it. Now, if I look over by increments, what would that end up being? If I look over by increments, rather than just saying the general gist of 1 and 1/2, let's break that down a little more. Another way we can divide fractions that we rarely talk about, right? We all want to say invert and multiply. Well, just hold your horses, just relax. What we want to do here is, why can't I just get equivalent fractions to match my denominator? So it'd be 3/4 divided by 2/4. If it's 3/4 divided by 2/4, look down here, 3/4 divided by 2/4. Do we all agree 1/2 is the same value as 2/4? Yes. So what's 4 divided by 4? 1. What's 3 divided by 2? Oh, I don't know. What, 3 halves, 1.5? That's how this ends up working. So what do? Set up where 3/4 is, and then show them how many 1/2s get in there. In this case, I've got 3 increments, right, over 2 increments. And why this happens is I'm representing how many of my 3/4 versus my 1/2. 3/4 divided by 1/2. My answer is going to be, if I match up increments, 3/4 divided by 2/4, 3/4 divided by 2/4, my answer is 3 halves, or 3 seconds, 3 divided by 2. I know it feels weird because you and I were always taught it's not for you to know why, just invert and multiply, right? Make sense of it and see, oh my gosh, I can see how many halves would go into it. And the answer is, in this case, 1, 2, 3 divided by 1, 2. it's going to be 3/2. But you can even do that at the abstract level and get better results this way. Okay. So your turn. If you don't mind, I'm going to look over questions. I'm going to give you just 30 seconds. Look them over. I'll show you example. I'll show you the answers in a second. Try one of them. Just give you a couple seconds on it. And I'm going to look through questions. Yes. Okay. So I think she asked it openly, so I'll answer it as you guys are working. Ms. Kaiser, you asked if there's a good online platform. Yes, I'm going to actually show you at the very end some implementation ideas. There are good online platforms that show length-based approaches. Matt, oh, I can't wait to see Dennis. Thank you. I can't check it, of course, now, but I will look. Yep, that's a good one. Thank you, Dennis. Do middle school math. Concrete models sometimes get them frustrated. memory erasers. Do take a look at some of the alternate computational approaches. You also can do, if you ever heard of cups and sticks approaches, it's called multisensory algebra. Who asked this question? Donna. Oh, you're right there, the face. But you can look up a just multisensory algebra. It's called it's used a discrete model. So like representing 4/5, you do 4 divided by and then do 5 bars and just do it computationally, right? Equivalent fraction, another numerator, another denominator. It's too much in this short amount of time, but we can talk another time. Honestly, just set it up and just say, hey, Brad, can you meet and show it? And I always have a doc camera here. Just pop it up. I'll show you step by step. Just send me an email. All right, let's go back to this, guys, for length-based approaches here. Oh, by the way, Donna, good Men in Black reference. Apologize. What's the bridge look like between number line and average? Oh, here we go. Okay, so first, Teresa's asking the connection between that number line model and the algorithm. Oh, exactly. So if you looked, as you're showing your number line model here, keep showing what's happening computationally between them. Don't just show number line models and say, I love it, Teresa. Say, rock on, go get them. Show what's happening mathematically. Explain that, okay, look here. We've got 3/4 divided by 1/2. It's another way of saying 1/2, it's 2/4. So how many 2/4 to make a whole, right? There's 2 of them. How many 3/4 go in here? And then that's where you get to say, oh gosh, I have 3. So here's my answer. I've got 3 of the increments divided by 2 of the increments. It's really all the magic that goes in there. But make them, see, didn't mean that. Make them verbalize that algorithm through the process. One of my friends actually says, Trisha Strickland, who I've done some work with, actually says she even writes out as she's doing the math model, the picture version, she writes beside it the algorithm. So they see how the picture always connects back. I love it. Great question. All right, let's take a look. 4/5 divided by 1/5. Nice and straightforward. Identify where 4/5 is here. Show your length that shows 4/5. And what are we dividing it by? 1/5. Right? In this case, there are 4 1/5 that go into 4/5. So a nice easy one here. It's 4/1, 4 divided by 1. Nice easy one in here, right? Do how many bar? What's the top bar? There are 4 of them here to check your work, but there goes 4 divided by 1. Okay, let's take a look. What? 1/3 divided by 1/2. Show the algorithm, just like you said, Teresa, show that algorithm. So instead of 1/3 divided by 1/2, right? This is where you find your least common multiples, right? And in this case, I'll show 6. If they get 12ths, it still works, right? But we can show here, and what's my equivalent? 2/6 divided by 3/6. All right, let's see. I don't know what that 2/3 is showing up here for. Oh, I know exactly. 6 divided by 6 is 1. 2 divided by 3 is 2/3. 2/3 divided by 1 is 2/3. All right, so here we go. Let's show this what it means on a visual as we're showing this. So we show 1/3 divided by 1/2. All these denominators. We fix that up to make it clean. 2/6 divided by 3/6. Now show where 2/6 is. So we represent where 2/6 is, and we're dividing that by what? 3/6. Okay, so what's my answer here? 6. We already have 6 covered, so the answer is 2/3. This length here is 2/3 the size of this length. So all you do is write down 2/3. Equivalent fractions makes that so clean. Okay, let's take a look at the next one. 1/6 divided by 3/2. Equivalent fraction shows me that this is 1/6 divided by 9/6. That is a doozy. I'm sure that really went well over the intercom, over your speakerphone, but that's a doozy. So let's make sense of this. We go by sixths here. We represent where 1/6 is. And now we represent 9/6. Yes, all this, but we've broken it down by sixths. So what's my answer in this case? This length is 1/9. The length of this length of the green. or whatever color it shows on your screen. But that is because, oopsies, and that's because that 1/6 length, it is that increment of it. So in other words, how many groups of them? I'd have to multiply this length times 9 in order to match that length. I'd have to multiply that length times 9 to match that length. Hope that makes sense in this. Fractions are an oopsie-doopsie. Make sure that you get that length-based model in there. Yes, Donna, I mentioned briefly, this is a less intensive mechanism for you're going, oh, I don't know that for my students. Your children might need a more intense approach. This length-based models is a low intensity approach. Discrete models or ratio fractions with the lines drawn and all the popsicle sticks, that's a more intensive model. Right. So let's get the computation on this one. Any questions on the length based with fractions? We're just ready to dive into the next step. All right, without further ado, let's talk about equations and go Betty. All right, here we go. So this is the abstract of where I want to go. It's a number, or X, depends on where you are in the learning mechanism, or the learning process of this, but a number plus 2 equals 6. Nice and easy one, even for students who are beyond this, who don't have any background in lengths, but I know they struggle with what I'm about to teach. I'll walk back and I'll even show them this so they're ready for that next step. So I set it up, and I'm gonna have to show in here, right, that subtracting to each side, oopsies, come on, Red. I'm gonna show that, right, the additive inverse to get to this answer. I don't just want them to guess what plus 2 equals 6. So we set up a length-based model. This is not size proportional. Remember, length-based, low intensity, right? So this is an intervention for the masses. We can go more intense at another time because again, this is just an hour and a touch. So in this case, I'm going to have 2 lengths. X plus 2 would be the same value as 6. So if X plus 2 is the same value as 6, I make them total to the same value. No, that doesn't look like 2 next to X. I don't know what X is, so I have to guess, okay? So I simply cut it down the middle. Some of you like to have mixed models in there. I've seen it done a dozen ways in different research studies. But in this case, what part whole model? Aaron, you rocked it. These are part whole models if you're used to that. There's another way to do it. I think it's called a total model. But anyway, different ways to do this. You'll see this in elementary levels when they're teaching 4 plus 2 equals 6. Here's our unknown version of it. So I asked them, what does X need to be to make each one of these lengths, right, the top and the bottom, the same? So, or the same value, apologize. So in this case, I need to do some math to figure that out. Now I'm going to teach my additive inverse. So in this case, I'm going to take each length, I'm going to take one of these terms, and I'm going to add one of the terms on top. I'm going to take away 2, and I'm going to take away 2 from one of the terms on the bottom. Since I don't know what X is, I'm going to take it from 2. This is what it looks like. Match it if you're a color coder. Match up the color coding as you're showing the abstract. Oh, so Teresa, we have not found that it is detrimental because again, we're doing the length-based initial, but the goal is here. And you got to have non-proportional work because you don't know what it is. So we haven't, anybody that shows proportional work, they're already giving away the answer before it starts. So next step here is, okay, what do I have then? What is 6 minus 2? It's 4. What is 2 minus 2? It's 0. So I have it here, 4 equals 4. You can even just take out this model and draw another one over or under it or over it, just so they see X equals 4, the answer is 4. Always have them go back and check their work. It's important so they can see the connection. All right, let's get a little more complex. X minus 7 equals 5. So I'm going to walk you through. I want you to step ahead of me on this one. You start drawing out, what do I do with -7? It's mind molding, right? Oh, right. I need someone from Star Trek to come in, right? Spock to give me some help here. But what we're going to do instead is we're going to set it up with that non-proportional. That's why you can't have proportionals, because negatives hard to represent. That's why the first grade teacher said you couldn't take 7 from 5. We're going to work through that and say these are just terms. The blocks aren't necessarily size proportional. Each one of these lengths is just a term. So in this case, 5 is the same length as X minus 7. What does X need to be? So now we set up same thing. Hopefully you're a step ahead of me. You did the additive inverse, one on the top bar, somewhere in the term on the bottom. So in this case, what do I have? I've got, you got it, 12. And then, sorry, I've got the work showing in front of me here. I've got 12, come on, and then X equals 12, 0. And yes, you can rewrite it as X equals 12 as well. So they see that. show them how this works, because what we want to do is then I get to the lesson of the day. Oopsie, excuse me, of course, check. Then I get to where we're getting closer to the lesson of the day. How about 2x equals 4, right? What does x need to be? So I show the multiplicative inverse in this case. Same thing, I've only got one term on top, one term on bottom. So I do multiplicative inverse here, all right? And one side and the other side. And then what does that show me? Well, what's 1/2 of 4? And then what's 1/2 of 2x? Oh my gosh, that may take some time in conversation. What is 2/2? But then go through and show. So if 1x equals 2, that means, yeah, x equals 2. Go back, check your work. So we want to keep building on them so they see this, so they can go into the 3x minus 4 equals 5. I'm showing you all the steps here, right? All the work that needs to go into this. So we ask, what does x need to be so that each top and bottom match up? In other words, one side of the equation matches the other side of the equation. It's the same value by matching, excuse me, is the same value as the other side. So what is 3x? What does x need to be in this case? Wow, that's too much for me to think about. So let's go through the same steps. First one is that additive inverse. We're going to add 4. Let's let at least, we want x to be alone. We want to isolate this term by itself. So we take that -4, let's add 4 here, and we're going to add 4 into our top term as well. So 5 plus 4, -4 plus 4. That gives us 9 is equal to 3x. Yes, you can have 3x plus 0, or I take out the 0 and then I would draw out 3x. You might even have to separate the x's so they see there are 3 groups of x, right? And say 3 groups of x if you do that. So they don't think it's xxx, right? That would be wrong. Now, multiplicative inverse. What do I do here? I'm going to take 1/3 of the 9 and 1/3 of the 3x. Same steps. We keep working until I can finally find out what is in 1x. And the length of 1x is 3. So there's lots of different ways to do this. You might even be thinking, wow, I could physically even draw these 3 out and then divide 9. Remember unit rate, what we did, to divide 9 out into 3 groups of 3. And then each x would be 3. And then show them multiplicative inverse and teach them what multiplicative inverse is through this process. So again, length-based model, low intensity, you're showing the steps and you're reinforcing computation on the side. So let's reflect and then we'll keep moving. What are some benefits? What are some drawbacks? And then what do we do about those drawbacks? Okay, so let's leave it. Let's go just about 30 seconds into the chat room. Benefits. Let's be happy first. Let's be happy people. It's still early in the morning. So we're going to go, what are the benefits of length-based models first? So write those out and then let's talk about those drawbacks. That's great. Love it, Teresa. You got it. Conceptual and procedural knowledge, step by step with each other, right? And you said procedural. As we know, we went step by step with the concept. Length-based, that's why it's a low intensity model. We're not trying to obscure the concept in low intensity models. Sometimes high intensity models, we are stuck obscuring the content. We're kind of lowering the content to get them back up to speed. I know it's not fun. It's what a lot of people argue we shouldn't be doing. But when you have kids who can't add, subtract, multiply, and divide, more intense models are needed. All right, so let's keep going back there. Yes, that observational and yes, that intuitive length-based piece. Steps are still displayed. Got it. Okay, what are some concerns with it? Like, I'm nervous about this. I worry that they're going to blank. If it's the length-based approach or they don't have value of concept, that would be one. Would it be easier? Oh, you wrote me privately. I won't do that loud. So the question was, if you're going to do that top and bottom, should you write out the terms this way first? So let's just go 3x plus, I can't remember that one, 3x plus 4 equals 9. Was that it? But write them out side by side, the lengths, and then show, look, they should be the same length. That's not a bad way of looking at it. That was from one person, that if they're going to have a hard time with that concept, that would help them through that. Another one in here, builds concept, sequential, fractions, R length. Dang right, love it. So area and discrete objects, good. So right now, these are only length-based models. That discrete objects is a second step in there, Donna, you're together with me. See, we've done this. We're on the same page. So that's that discrete model of showing what it is. It still is procedural, but it will be less concept. So when you grow in intensity, you hope they had the background in the concept so we can get to a direct procedural approach. Yes, yes, Teresa. I get pushback on this stuff, Teresa. I'm writing an entire a couple states want this, but we've agreed. Me and Sarah Powell are agreeing to do a state's all PD across the state. Every teacher must be certified in this approach, and we're doing this for high school. And you should see the pushback of, I don't get it, and you're like, how do you not get it? Wait, do you not want to get it, or sometimes we just need to move our cheese and catch up. All right, here we go. Here we go. Yes, Jason. Oh, apologize. It just moved on me. Catherine said in there, if you don't see this, showing a different model than what is in core is sometimes confusing. Ding, ding, ding. We need to sometimes co-teach with core so that our core at the same time, we are working on a solo taxonomy. If you've ever done this, if Jared's out there, you know about solo, go Jared. But we want a core approach that everybody is using so we can match the intervention to it. Sometimes we find everybody's got a little different way to go. And there's where the cups and sticks comes in, Jason. Ding, ding, ding. I love that. That's the more intense work that Donna, you may have heard. All right, guys, for time, I got to move into Jean-Claude Van Damme dancing, which is just wow. Okay, my wife always said he's hot, and I go, well, watch this. I'll ruin it for you. Anyway, so that was the killer for her. All right, so here we go, guys. Let's talk about area model. Let's talk about factoring. Oof, that's just dangerous. Okay, in the last session, we talked about using the area model to show distributed property, which really is just showing multiplication. In this case of binomials, we could do, of course, general polynomials as well, or at least co-plan, Amanda. Thank you, Amanda, for clearing up what I said. I'm a big pusher of co-teaching. I know it's financially not always advisable in some districts, but I even have poor teachers will push it because it helps inform core of what the intervention is if we have a huge group who needs intervention. All right, take a look at this one. We said earlier, 3x times 4x, right? It's just, if you've ever had to do the bunny ears, the nose and the mouth, or what is it? Eyebrow, nose, mouth. Or you've ever said FOIL, which only works for binomials. Please don't say FOIL. It's the distributed property. FOIL does not work past binomials. Like when we go here, FOIL falls apart. So, oopsie, sorry, Jean-Claude. But we want to show an approach that works for future work. So in this case, 3x, here's a terms, here's a term, here's a term. Remember length-based? 3x minus 1. All right. So we go at 4x plus 5. So what is 5 times 3x? 5 times 3 is 15. 1's times x's is x. 4x times 3x. 4 times 3 is 12. X times x is x squared. Remember, when this was a 10, it was 10 squared, which was 100. So we've got different ways of showing this, and then you add up your terms, your like terms. If that works for you, and polynomials work for you, right? 2x squared times 7x, 2 times 7 is 14, x times x squared is x cubed, right? And then you add up your like terms and you can summarize. Oh, the Punnett square, absolutely. It does translate the science very well because again, right? The claw, oh my gosh, for the FOIL wannabe. Oh, I love it. All right, so there's lots of ways it works with each other, but this one holds true across. Length-based works across multiple content. Area works across multiple content. So this is one, right? If I have another expression over here, yeah, you'd have to go 3D, but you could still do it. 3D chess is hard, but okay, we're going to take that same approach and let's start factoring. To build into factoring, we're going to do long division. I'm trying to read this at the same time. We're going to build in long division on this one. So I'm going to figure out how many groups of x plus 4 go into x squared plus 7x plus 12, that expression. So I mark here. It doesn't matter what manipulative set you have. If you like algebra tiles, if you have, let's see, it'll show up on the camera. If you do based in blocks, you can't really see it, but I have so many writings on this. It looks like a student or somebody wrote x squared on it at one point. My x's, if you look too closely, they have little writings. Some people write x, like this is an x term. It's just to give a visual to it. All we want is a physical visual that fits this. So in this case, this is a real clean one, right? Ms. Kaiser, you know this is a clean, direct way of doing it. I represent x squared plus 7x plus 12, the constant. So what I need to do is I need to figure out how many x plus 4s go in here. Now these will pop up here, guys, as base 10 blocks. I caution using another base 10 block set up here unless you have, show this here, unless you have a board. I don't know if it's going to show because it's shiny. It's shiny. Unless you have a board that shows that hangman T, that awkward T chart. If you have that board, you're in good shape. If not, just be cautious because students who are sloppy blocks will move, I would draw it out. So let me talk about what I mean here. I'm dividing by x plus 4. I would draw these out to be a length, dot, 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 and then move in two of those terms in there. And one group of that would be x squared plus 4x, right? I know that that will fit that x plus 4 cleanly, which means right now, what's one of my factors? Draw it out. Now, again, it's going to show up nice and clean, but remember, draw out the x to make that clean. As you're doing it, look, the abstract, you're doing the abstract at the same time. So they do a movement, you show a movement, then you say, okay, guys, so x works. What's left over? They see 3x plus 12. You do the multiplication and subtraction here to show why 3x plus 12 is remaining. Okay. Next one. Oh, specially designed instruction language. Ding, ding, ding. Okay, sorry, Cody. Yes, Jody, excuse me. So same thing. I'm going to keep working through this. I have another term that I find in here, and we'll get to it. So I go x plus 4, which means I have at least one more divides into it. Now, why does x plus 1 work? Right? You're going, well, that's not the answer. Yes, it is. You can stack your answers and keep working. Right? Now I've got how many? Why do I have 2x plus 8 left? Well, guess what? That's going to be clean. 2x plus 8 works fine. And really, it's just another factor of 2 in there. So now I get to find my factors and work it out step by step through it. What I'm doing with this, if you're using specially designed instruction, that means you're using explicit instruction on this. I got visuals to support my student. Some students will need this, where other students are able to just do the abstract. While I may have stations going on, one station's working on this for specific students, manned by me, or if I'm co-teaching, I can man that station. While an independent station, maybe I've got them working on the abstract for certain students. And some students will come back and rotate to me. There are ways to set this up to give that specially designed instruction to those who need it. Okay, let's try another one here. Oopsies. Oh, sorry. Then my answer is make sure that they see the entire answer worked out. So it's not x plus 2 plus 1. Make sure they know that combining like terms, it's really x plus 3. All right. So for time's sake, let me sprint a little bit. Think about how one of these is done. Try it on your own in practice. I'm going to go right into factoring so you can see how this is done. But jump into this and see, wait, how would I do this? So I don't have time to wait and watch. A full training would mean that you would be with me. We would do this together until you were clean with it, and everybody in the room could do this. Because if like I'm getting that direct message about specially designed instruction, I don't need that just for a select few. Not just the math coach should be doing SDI or specially designed instruction. I need to make sure those strategies are with everybody so we all can interchange them to team teach as best as possible. All right, here we go. Talk about visuals. I'm going to take this same approach and I'm going to talk about factoring. So when factoring, you want to multiply the A and C terms. I know just the steps. Hold on, just the steps. Don't memorize. I know you're taking pictures, but we're going to physically walk through this together. You're going to multiply the A and C term, determine potential factors that you get out of this A and C term multiplication, right? Out of that product. Then we're going to select the factors that can add to be our B term, then find the greatest common factors among columns and rows. Whew, if you think that's long, guys, memorize the quadratic formula. That's even uglier. So we're going to take the quadratic formula and break it into these steps. So here we go. Step 1, and we're going to teach them. Students cannot learn, the average student is not going to learn more than 3 steps at a time. So this is at least 4 plus the extra work with determining which ones add to be the B term. Just a warning, you may be teaching step 1 and 2, stop. Another problem, step 1 and 2, stop. Another problem, step 1 and 2, before you go back and finish the work. Teach them based on their memory. So here we go. Multiply the A and C term, which means I'm multiplying 3x squared and -1. What am I going to get? -3x squared. Okay, that's step 1. Step 2, I'm going to determine, and why is that? Because I'm trying to determine what fits my square. If you remember, I'm trying to determine that 3x, those are big 3x squares. 3 of these blocks, I'm trying to determine how I'm going to break apart those 3 blocks into that area. So this is the same model. Look, the x squares go here, the x's will go here, and my constant goes here, just like we did the last model. So now determine your potential factors. What would, right, multiply to be -3x squared? So I've got, and knowing that I still need x's and x's here, right? So I've got 1x and -3x, okay? Or -1x and 3x, right? Okay, both of these both include the same, right? The same variable, and right, that means they would multiply to be x squared, and they and they would also multiply to be the -3, right, for the coefficients. So it works. stop. I would say practice that for a while with multiple problems and then get to these two steps. Determine the potential factors, right? So that was 2. These 2 steps now are which one of these adds to be your middle term, because it needs to add up in this horizontal, excuse me, in this diagonal way here. So in this case, how about 1x and negative 3x? If I were to subtract these, or excuse me, if I was to add these, it'd be negative 2x. Negative 1x and 3x. That would add to be positive 2x. Positive 2x. Guess what? I've determined my terms. Or my, excuse me, I've determined my factors. So what am I doing here now? It doesn't matter what order you put them in because they still multiply correctly. So in this case, I put them in, and this is my last step. What's the common factor between 3x squared and 3x? It's 3x. What's common between, right, negative 1x and negative 1? It's negative 1 is the only thing I can see that's common here. How about what's common between 3x squared and 1x? I see x, and that's it, just 1x. And what's common between 3x and negative 1? Oh, I don't know. I guess 1? It's not negative 1, so I guess 1 is always there. Guys, you've just determined your factors for 3x squared plus 2x minus 1. So in this case, you go through your steps. Oopsies. So those are your terms. Check them by multiplying. You can do this, either put it as your array model and remultiply it. It already is, and make them multiply it back. You can do base 10 blocks and bring out the base 10 blocks or algebra blocks to check it, but let them go through and really figure that out. Okay, your turn. I'm gonna let you work because we're shorter on time. So just work a couple steps ahead. Try this or write it down on your own and go through the steps. I'm gonna go one step behind you. So 1x squared plus 3x minus 10. Step 1, you should be multiplying the a and c terms. Okay, here we go. If you're to do that, you should get negative 10 x squared. Come on, x squared didn't show up. Negative 10 x squared. X squared is not showing up. All right, determine the potential factors of negative 10x squared. What are they? They're going to be, oopsies, hold on. They're going to be 10x and 1x, negative 5, and it's negative 10, right? So yeah, negative 10x and 1x, negative 5x and 2x, 10x and negative 1x, or 5x and negative 2x, right? Set them up. Which of these factors add up? There we go. Which of these factors add up to be positive 3? And that would be 5 minus 2, my 5x and negative 2x, they add up to be positive 3x. Write those terms in, and then the greatest common factor of each one of these, just factor 1x squared, negative 2x. So what's this going to be? 1x? Yep, 5x and negative 10, so it's going to be 5 here. In this case, 1x squared and 5x is going to be 1x here. And negative 2x and negative 10 is going to be negative 2. Let's see. There we go. So you can take factoring, break it down into that same area model physically. Use, if they have the background in that physical model, you could then use it for this approach. If they don't have a background, my suggestion is start with this approach at the concrete level and then show them how this all works, but stick with the steps and make it logic. All right. So again, you get to work through any of these, try them on your own. I'll just take a picture, try it on your own for time. I do not have, I don't think I clicked the answers, no. So that is just going through and figuring out. I think you're going to see where it goes. It's probably going to be negative 3 and it's going to be x minus 3x minus 2, but you go through, figure that out of how you get to that answer, but I leave you with that. Try it on your own. You got it. Everybody's saying, I haven't tried this. I'm going to give it a shot. Practice ones that have a nice A coefficient first and then get more complex as time goes on. Remember, it comes down to understanding your steps and the visual of what we're trying to do. All right, are there questions about the area model and factoring and how to build on that factoring model? I'll go there and then we're going to problem solving, and then I'll probably have to wrap up just by showing you some of the features online that you can find that will guide you through these problem solving steps. You got it, Ms. Kaiser, because as we go through, because I think everybody can see it. Yeah. And same thing I see, right? I hope you're a farmer if I see that, right? Cattle farmer, as I work in the Midwest a lot. But as you're working through these, you'll see that this has been highly effective for students who lack some of those early computational work at the concrete level. For those who have strong computational backgrounds, they just can't memorize all the steps of this stuff. Think about breaking it down by small steps, chunking it, and I should say not or, And with chunking it, if you need to go more intense, show the visual model that builds on that. Love it. Oh, there you go. Woo-woo. Penn State. Beneficial. Do you think it's more beneficial for students to understand polynomial division before they see? I actually do. I think that understanding how it breaks down to division, showing one factor before they work on multiple factors. I just see, to me, Elizabeth, I see that as a step progression. Of course, some students can take conceptual leaps where others can't. I had one student named Eric who really struggled with me, hated math coming into me in middle school. So we actually showed how things worked at a later level. As a tutoring thing in university level, we tutored him to help him through see it all. He had severe dyscalculia. I'm old, right? So it's now it's got to be about maybe 15 years later, maybe 20 years later. Wow, I'm getting old. He is now a head engineer down in the Tampa area. So I can say he figured out the mathematics behind it. Concrete learning of math will not dumb down as long as you stick to that algorithmic approach. I've got lots of stories like that. Cool ideas. But I don't see polynomial division until the last unit of algebra 2, which means we can talk about how, instead of just getting to polynomial division, show earlier factoring, easy basic factoring with the concrete model, visual abstract, and then, Elizabeth, build it into that later on. See, I see it differently, but that's okay. Different textbooks, different approaches. Okay, let's talk about problem solving here. This is the big ugly that a lot of people say, how do I get kids to solve this? So we showed you Jonte Meyer's work, his meta-analysis of multiple studies, high effect studies, well-done studies, core tier, top tier studies, ones that do not have a lot of errors. There's a lot of studies with a lot of errors. And Myers is real good at not including those. If you read his work, he even tells you not the names of the studies. He's polite. He's a friendly Caribbean guy, and he won't tell you the names of studies he eliminates, but he'll just say, we looked at 123 studies, and after eliminating studies that did not include blank, 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 blank. And he goes through all the things like it uses a researcher-based approach, or the researcher wrote their own assessment. Once eliminating all these studies, we have 65 studies that meet criteria. Then he tells you, he found general heuristics, a stepwise approach, teaching step by step, has a very high effect size for secondary math. In this case, solve. UPS check someone wrote in the last session, UPS check, based on the same process. I'm going to choose solve because it came up frequently in a lot of the studies. Doesn't mean it's the only general heuristic that's out there. Heuristic, stepwise approach, like a strategy-based instruction. That's what a heuristic is. So but it works across multiple constructs. Solve works across multiple constructs. We'll be teaching students to study and read. Listen, POLV doesn't work, but I really want them to paraphrase the problem. But again, POLVE doesn't sound good. So study and paraphrase. How about that? The problem. But we do want them to read it. A lot of students scan problems, make them read it, and then paraphrase it. Organize the facts, underline what's important, right? What's extraneous, what meets the problem set. Line up your plan and explain your plan. Verify the plan by doing the computation and explaining how it met your plan, and then go back to the problem. Does it make reasonable sense? They don't have a background in the content that in the word problem, they're not going to know if it makes reasonable sense. But in some cases they do. So let's talk. Here's an example. The length of the garden is 8 feet more than the width. The area of the garden is 240 square feet. What's the width of the garden? So what do we do in solve? We take this, and what a cute picture. Thank you to the team who put that in there for me. But what we do is we're going to go under S, it's supposed to be highlight. Come on, it doesn't highlight. There we go. SOLVE. So we set this up. We know it's a rectangular garden, right? The area, because they only talk about length and width. That's stuff that we're pulling from the problem. Do you think it's a circle garden? Do you think it's a hexagon? Do you think it's a parallelogram? Well, maybe, right? But we're going to do length and width. And then let's get into the details. Next, we're going to underline its length and width. These are my indicators. These are how I made my claim. This is what shows my claim makes sense. 8 feet more than in the area. So something plus 8, right? And I've got the width. We don't know the width, and it's 8 more than the width. And the area is 240. I should probably write square feet in here, my fault. But that's how we set it up. Now, I start to organize my visual, and I set up my visual. Then you connect your visual. See, CVA still works. Connect your visual to your computational approach. set up your plan, your computational plan. Does it make sense with the visual? You can even have students stop at S, stop and explain, turn to your partner, turn to your small group, talk to me. Oh, same thing, right? Talk to me, talk to your partner, talk to your group. Same thing as computation. Have them set, check, check. If you want, you can put numberless word problems in there just to make sure that they're actually following SOLVE. You can take out the number and put in Q, right? You can take out a number and put in squiggly line or star, but whatever you put in there, it makes them, you want them to talk through the process as much as they think about the computation. All right, next up, now that we've got my plan figured out, we verify the plan with computation. They set it through that way, they explain it. Then let them talk through factoring. What does it mean to factor, right? Because I end up with this crazy, right? This crazy quadratic in here, and it's, right? The width squared plus 8 times the width minus 240. Oh my gosh, Brad, I don't know what's going on. Well, yeah, I agree. The reason why it's squared is because it's F's, right? It's feet squared. I think we did feet, right? It's feet squared. Reason why there's no squared, it's just feet. And the reason why this is already feet squared, because there's no feet in there. So in this case, we, right, it doesn't automatically list it. So in this case, we walk through and we show, is there a greatest common factor? None that I can find cleanly. Okay, then can we group, right? If you like the word foil, then you should like the word unfoil. So we're going to unfactor it in this case. And in this case, we're going to figure out what are the factors of, and that's where we go back through and do that computation. So yes, you can go back through, you can figure out first, outer, inner, last if you feel like it. You can do, again, not my favorite choice, but you can also go back through and you can actually do your grid, your area model, go back through it and connect it to it. Consider your factors and what works. Some students will use guess and check on you. Other students can actually get through and do that step approach. You can even pull out the base 10 blocks and get through it. Timeout warning, don't give a problem that has 240 square feet. If you're using base 10 blocks, make it 12 square feet, make it 16 square feet. Don't make them count out 240 in your constant if they're at the concrete level. So that would be an adaptation, an accommodation, not a modification. They still have to learn the construct, but you can actually help a student through, but with a concrete step if you change over the numbers so that it works cleanly or more to their level. All right, last steps here. Examine if it makes sense. If the width is 12, is the other one 20? Does that make sense to have the length be 20 and the width be 12? Talk, is it, right? It is not possible to have a negative width, right? If you do the factoring and you get a negative width in there, they should go, well, I can't get a negative width. It makes no sense, right? So in this case, it's going to have to be 12. So we go back through, make sense of it, have them explain the size of the garden. They can even sketch it out. It is an area model. In other words, if I'm going to start with an area model, I'm going to show the physical area model. I'm going to make my word problems fit an area model because I want them to see the connection. We can get more complex as time goes on and their computational competence builds or their factoring competence builds, but I've got to start somewhere for them. All right, so if you don't mind, if we do a little break, just a little talk, and then we'll do 1 or 2 minutes, wrap it up, and then I'll let Julie take over. Tell me the pros and cons. Let's start with the happy thoughts. What is a pro of the solve approach? What is so beneficial of going this approach? Especially if we all do the same approach. If Jason, Pam, and I are all on a team and we all use solve across our whole school, what is a benefit of using that same heuristic across the school? I agree with you, Dennis. They can build, and we can take this in middle school. We can take this earlier. We can build in that common language. We always have a starting point. Like you said, Laura, if they take it there, we can even let them expand to get more complex as it goes on, because solve is your starting block. I like how you put that, right? Oh, cubes. Oh, so go R cubes, make them read the problem first, R cubes. Same general heuristic approach. I actually work with a school that uses R cubes, read, then cubes. I have another school that uses UPS check. I have another school that uses solve. It's as long as we have a team agreement, we've got a common heuristic, we can all go after that. Got it. And practice consistent performance. Love it. That's what Sarah said. Oh, if you got to hear my friend Sarah. Yes. Yes. Oh, you're talking about the R cubes. You can tell we've worked together a couple years. All right. So we've got some of this down. Please continue through and look at solve. Now, in my 1 minute, Julie, if you don't mind, I love that dance. That's the Elaine. You go, girl. Get that Elaine going. Okay, I don't know what's in her hand. I'm sure it's water. So instructional considerations here. And as we build this up, right, I want you to think about it. One, you guys are already writing it in there, right? Mary's already got it in there. One, we need consistent routines across content grade, right? Horizontal planning and vertical. We need to inter-scaffold within a lesson. We need to intra-scaffold lesson to lesson, year to year. Yes, I know we have a transient population in this world, but we've got to be consistent. If we could be consistent across one district, that would be amazing, let alone one state, let alone one country. But we need that consistency in there. Here's some other strategies I would like you to consider. Build visuals with explicit instruction. It's not I do it, we do it, you do it alone. Those are nice starting blocks. One state I work with, they call it me, we, to you. Me, eyes up front, watch me. We, back and forth communication. It's a didactic approach. Two, partner work or triad work, and then you, independent. I like that. Make sure you add in other elements of explicit instruction as students need that intensity ramped up for them, right? There are 16 elements, so you can add more. Whoopsies. Oh, you guys asked about virtuals. There are great ones out there. I think the Wi-Fi or whiteboard.fi is great. Braining Camp's got good ones. Didax. Desmos and Didax. Didax really, for me, has a great manipulative set online. You can actually use the manipulative objects we did there at a visual level. And Uplift is a newer one. I really like what it's Mahul Shah. I really like what Mahul's done with Uplift. They have a free and they have a paid, like all these, they always a free and a paid. They have there, and they have really sharply done visuals on Uplift, and they can even measure your students guessing. They can measure the cursor movement to see, are they making good thoughts to it? Are they deciding right when they move things across and you see them moving that cursor? Are they moving in the stuff in the right area before they correct? In other words, are they self-correcting or not? There are cool things with Uplift, but great ideas. Last one's in here. CVAS plan, teach it step by step, prep it from the very beginning. I am done, Julie. Only 2 minutes over where I said I would be. I thought I did well. That is the best dance of the night. I don't know why there's a moped parked in their living room, but don't ask behind it. It's a cute dog. But guys, if you don't mind, as Julie's talking and gives you that summation, use the chat, give me some feedback, things that work, things that you're excited about.